There we go. These next two chapters are very related. They are both on acids and bases. Chapter 14 is more about the properties of acids and bases and also how we define acids and bases. There's going to be 3 different ways to define what is an acid and what is a base. So we'll be going over that. And then in chapter 15, it's about the pH scale and where that comes from, what it's based on, how to calculate pH from concentrations of hydronium and hydroxide ions. So it's all related. I don't think this is going to take us to the end of the year. I'm pretty sure I'll be able to fit another chapter in after this, but we'll see. Because don't forget, we got some catching up to do for bio as well. Anyway, let's start. Today's topic is just going to be the properties of acids and bases. Now, I'm sure that most of you have heard of at least some basic properties. For example, the pH of acids is below 7. The pH of bases is above 7. Maybe you remember that acids are sour, bases are bitter. But yeah, we're going to go through the properties of each. So starting with acids. Now, a lot of foods have acids in them. For example, sour milk is lactic acid. Vinegar is acetic acid. Citrus fruits have citric acid. Apples contain malic acid, and grape juice contains tartaric acid. Now, if you think of what is common between all of these different foods, the one property you might think of is sour. And a lot of household items are bases. For example, ammonia. A lot of cleaning products contain ammonia or ammonia-based compounds. We have sodium hydroxide, which is also called lye. That is in drain and oven cleaners. And we have something called milk of magnesia or antacid, which is magnesium hydroxide, which is used to relieve stomach pain. You can think Antasil or Eno. They are both alkaline solutions because you take these when you have stomach pain, because stomach pain is usually due to the overproduction of acid in the stomach. Hold on a second. Set bean in. So stomach pain is usually due, like I said, to the overproduction of stomach acid. And so you take something like Eno or the little chewable kind of chalky mentholy tablets called Antasil to help relieve or neutralize that excess stomach acid. So here on the left-hand side, we have some common food items that are acidic. We've got apple juice, coffee, strawberries, and of course, lemon. Lemon contains both citrus and ascorbic acid. That's what makes them super sour. Coffee, or is it carbonated beverage? Maybe that's Coke. I think that's, oh yeah, carbonic acid. So that's Coca-Cola or Pepsi, whatever. Look at all of the acids that it contains. Benzoic acid, you can see a little bit of, what do you call that? Organic chemistry is when you see COOH, those are carboxylic acid. They are organic acids, and that's usually, what do you call that? Denoted by the ending oic acid. And you'll learn all about that next year. Ascorbic acid, again, you've got phosphoric acid and carbonic acid, all of those that are in carbonated beverages like Coke or Pepsi. And that's the reason why they're very corrosive to your teeth, among other things. And then on the right-hand side, of course, we have a lot of household cleaning products. In America, we have something, it's a brand name called Tums. These are like your Antasil. I think that's how it's spelled. Antasil, and whatever. It comes in strips, right? They're little yellow tablets that you chew when you have an upset stomach. Okay, and of course, baking soda, which is also, it's used in cooking, but also a very good cleaning agent as well. All right, so going through acids first, they were first recognized as a separate class of compounds because of the properties that they have when they are in aqueous solutions. So property number one, of course, is a sour taste, although this should never, ever be used as a test to evaluate a chemical substance. You don't ever want to use tasting or even smell. One of the ways that you can evaluate smell in a lab is by doing something called wafting. And wafting is when you hold like the test tube or the beaker or whatever in front of you, and you take your other hand and you just kind of waft the air in your general direction. You do that because you don't want to put your nose directly above or in a beaker or a test tube, just in case there are some volatile or corrosive caustic materials in that test tube, or let's say, I don't know, poisonous gas that's being created by whatever chemical reaction. I worked with a guy once, and I can't even remember if I was able to, I don't think I was ever able to teach you guys pipetting. Maybe we did it when we got back to school, because both your grade 10 and grade 11 years were started with online learning because of COVID. But usually in the summer school before grade 10 is when I teach a lot of lab skills, and the most important one being pipetting. That's when you take your pipette with the bulb on top and put it on there. I do think that I've ordered, I don't know what you call them. They're instruments that are easier to pipette with. So you put it on top, and then you have a little wheel that you roll up, and it gradually pulls it up instead of having to squeeze, put the bulb on and let go. Anyway, my first job out of university, I was working in a lab with a guy whose all of his front teeth were like half dissolved and like brown and half rotted, because when he was younger, he mouth pipetted. So, you know, the pipette is that hollow tube that you use to transfer volume of liquid from one thing to another. And it's open at the top and the bottom. It's graduated. And he used his mouth to suck up, I think it was some kind of acid, to transfer it, but he sucked too hard. Of course, it went all up in his mouth, dissolved half of his teeth. So don't ever do that. Mostly because, as my colleague found out, that many acids are corrosive. Now, there are two different words to describe what are basically the same effects for both acid and base. Acids we call corrosive. Corrosive means they destroy tissue and or clothing. We're going to use a different word, but to describe the same kind of action for bases, and I'll let you know when we get there. A lot of acids are poisonous. Property number two, acids change the color of acid-base indicators. The general color that is associated with acids is red. So in this picture that you see here, they're using pH paper. pH paper uses universal indicator, which has a pH range of either 0 or 1, I think 1 to 14. So it's universal indicator is basically a combination of a bunch of different indicators. Okay, Bluetooth connection lost. Because different indicators turn color at different pH intervals. We'll learn about that as well. But yeah, universal indicator is for the whole pH scale. Some acids react with active metals to release hydrogen gas. Now, we learned about this last year when we studied the types of reaction, especially single replacement reaction or single displacement reactions with certain acids, metals that are above hydrogen in the activity series. The activity series is a list of metals and reactivity. So you've got like lithium, potassium. Actually, it should be Yeah, lithium, and then I think sodium and potassium, or the other way around, potassium's at the top. I can't remember. Whatever. And then down here, you've got hydrogen. I think zinc is up here somewhere. And you've got like copper, gold, silver, and platinum. So anything above hydrogen can go through a single replacement reaction with acids and release hydrogen gas. So an example, oops, I mean to go down. An example might be zinc solid plus, let's say, hydrochloric acid, Q. You're going to have the zinc replace the hydrogen. So you're going to end up with zinc chloride, which is aqueous, and hydrogen gas. And you want to balance that out. I should probably make my 2's look different than my z's. There we go. So that is a property of acids. Number 4. Acids react with bases to produce salts and water. Now, it's important that we distinguish between salt and salts. Okay? Salt is sodium chloride. Salt is a class of compounds, ionic compounds, that are produced during neutralization reactions with acids and bases. Okay, so salts are not the same as salt. I don't know why we had to make that so complicated by naming sodium chloride salt. So when equal amounts of acids and bases are reacted together, their properties as acids and bases disappear because that's called a neutralization reaction. And again, it produces water and an ionic compound, which is known as a salt. All right. Number 5, some acids conduct electric current. This is because strong acids ionize greatly in solution. Now that comes back to, what chapter was that? 13, ions in aqueous solutions and colligative properties. When we talked about electrolytes versus non-electrolytes, the only thing that you need to be a conductor of electricity is charged particles that are able to move around. So if there are strong acids are going to ionize completely. And so they're going to form a high concentration of ions. If you have weak acids, especially the organic acids like acetic acid, carbonic acid, things like that, they are weak acids, so they're not going to ionize as much as strong acids, so they will be weak electrolytes. Again, forming ions in aqueous solutions. Oops, that is spelled wrong. Let me fix that. Electrolytes, there we go. Try to fix my typos. So that just depends on the strength of the acid. Okay, that will be one of the things that we discuss later on between acids and strong acids and weak acids. Now, there's 2 main types of acid, and naming them is going to be based on whether they are a binary acid or an oxyacid. Oxyacids are the most common, and I've got a trick to remember how to name them based on the polyatomic ion that they form when they are ionized. But we'll start with a binary acid. Binary, of course, means 2. So one of them has to be hydrogen. And the other element is going to be one of the more electronegative elements. So any of the halogens, sulfur, phosphorus, I think that's it. Okay, hydrogen halides, HF, HCl, HBr, and HI. So I guess sulfur may be the only other one. The way that you name them, you can probably figure it out just by looking at the list of acid names here. So HF, hydrofluoric acid, HCl, hydrochloric acid, HBr, hydrobromic acid. So in each of these, you see that there is the root element name. Can I move that? Oh, I can't. No. And sulfur. Okay, so those are the root element names. So what do you have left? You've got hydroic acid, hydroic acid, hydroic acid. Well, we cut out the O because it starts with a vowel. Ic acid, same thing. So when you name binary acids, you have to have the prefix hydro, the root of the element ic acid. Okay, these are the main 5. I don't know if there's any other one besides these. Okay, the name begins with hydro, the root of the element, and then ic, and of course acid because it's an acid. The majority of the acids that you know of are called the oxyacids. These are hydrogen, oxygen, and a third element, usually a non-metal. I like to describe these, even though they're not formed this way, I like to describe these as hydrogen plus a non-metal polyatomic ion. I find for myself, it's easier to remember them this way, even though, again, like I said, they're not formed this way, but it's easy to name it this way. So for example, nitric acid is HNO3. So I look at this as nitrate, which is NO3 minus, and then enough hydrogen to neutralize that negative charge. So that would be 1 hydrogen. Okay. So these are also called ternary acids because they contain 3 elements, although honestly, that's not that important. Right. So this is what I usually use to remember it. It's 1 or more hydrogens followed by the polyatomic ion. And this is how I actually remember how to name them. Let me go back here. Okay, maybe I'll skip. Oi, here we go. Okay, so I just need a blank screen so I can get here. All right, so I've got NO2, NO3, nitrite, nitrate. Now, the way that I remember how to name oxyacids, I remember the rule ite, us, ate, ic. So if the polyatomic name ends with ITE, the acid name ends with us. So if I have nitrite and I add a hydrogen, this becomes nitrous acid. If it ends with ate, nitric acid. Okay, you can do the same thing with any of the polyatomic ions. Let's say SO3, SO4. This is sulfite, sulfate. So if I have H2, SO3, right? I need 2 hydrogens to neutralize the -2 charge on sulfite. This is called sulfurous acid, ite us. Sulfate, H2SO4, sulfuric acid. Now, the only problem comes in with the chlorine group, because the chlorine group, you have ClO minus, ClO2 minus, ClO3 minus, and ClO4 minus, right? So it's going to be a little bit more complicated, but not really, because the name of ClO minus is hypochlorite. So the rule itis atic still applies, but you just have to remember to include the prefix of the ion as well. So HClO becomes hypochlor. Oh, great. And my iPad just disconnected. Awesome. Anyway, I'll go back to this one. So, okay, iPad just doesn't want to work now. So you can see starting On the left-hand side, we've got the name of the oxyacid. There we go, back online. So if we go from the oxyacid, from the oxyanion, so hypo, what if I just put in chlor? Oops, chlor here, because that's the only group that we're talking about, right? The only thing we're missing is the root. So hypochlorite is ClO minus, and HClO minus is hypochlorous acid. Chlorite, ClO2 minus. HClO2 is chlorous acid. Chlorate is forgot my L's. ClO3 minus is chlorate. So HClO3 is chloric acid. And then finally, perchlorate is ClO4 minus. So HClO4 minus is perchloric acid. Okay, you just keep the prefix for that particular group. And here's a list of all of the oxyacids and the anion name that they come from. But again, they're not formed by taking, for example, chlorate and adding a hydrogen and boom, you've got chloric acid. It's more about water reacting with a non-metal oxide. Okay, there. All right, let's get that rid of that. Right, and so now, I got 10 o'clock, no, 11, yeah, 10 o'clock. Right, so then now I just want to run through, I think, 5 common industrial acids. It's not really super important that you remember everything, but it's just kind of to give you an idea of acids that are important for industry and why. So kind of like the, why should I give a crap about acids in real life? Well, here's why, because these acids are used to make a lot of common household items, and that's why they're important. So I'm going to go through sulfuric, nitric, phosphoric, hydrochloric, and acetic. Sulfuric acid is the most commonly produced industrial chemical in the world. Who cares how much is made in the US? They're used mostly in petroleum refining and metallurgy. Why do we care about petroleum refining? Because we get tons of products from petroleum, which is the crude oil, that black sludge that we take out of the ground, including methane, gasoline, diesel, paraffin wax. I forget, there's just a ton of products that we get out of that. And sulfuric acid is used there. Metallurgy is basically anything to do with metals, whether it's cleaning the inside surfaces of metal machines or whatever. Sulfuric acid is also used in manufacturing fertilizer, which is important, of course, for the agriculture industry. We also use sulfuric acids in making metals, making paper, paint, dyes, and detergents. Okay, so obviously, thinking about this, we all use detergents to either clean our dishes or wash our clothes. We all wear clothes that are dyed. We use paper, obviously. So very, very important. And a lot of chemical raw materials that are used in other industries, like the pharmaceutical industries, are made using sulfuric acid. That's why it's the most widely used acid. Of course, it is the acid that's used in car batteries. So obviously, if you drive a car or you get driven around in a car or rely on a car in any way, shape, or form, the battery relies on sulfuric acid. Because it attracts water, concentrated sulfuric acid is also an effective dehydration agent. So it can it can remove water from gases that it doesn't react with. Can't really think of a situation where that would be useful, but I'm sure there are. Maybe I'll look that up and let you know later how we use it as a dehydration. But any process where we can't use, let's say, heat to dehydrate something, we could use sulfuric acid to do that. Okay, next is nitric acid. Nitric acid pure is very volatile. It is a very unstable liquid that's rarely used in industries or labs. I've actually worked with concentrated nitric acid. I ruined my absolute favorite sweater at a university because I spilled like literally 3 drops of nitric acid on the sleeve. I was doing a nitrogen assay, or was it fluoride? I was doing a fluoride assay. I was working in a lab that was attached to a factory that produced pharmaceutical pills, but also was in a cooperative agreement with a toothpaste company. So I was testing the toothpaste for the amount of fluoride in it, and I needed concentrated nitric acid to test for the amount of fluoride in the toothpaste. Anyway, it stains proteins yellow. So here you can see a feather, which of course is made of protein. The protein is keratin. It's the same protein that is in our hair and our fingernails and our skin. It's also in feathers. And you can see when you dip it in nitric acid, it turns it yellow. I can also report that nitric acid has a very particular strong smell to it, which is why when you use it, you can't use it out in the open in a lab. It has to be used underneath a vacuum hood. There we go. Suffocating odor. It also stains the skin, and of course it causes serious burns, but it is used in making explosives. You might think, why do we need explosives? Well, the military uses it. Mining companies use it. It's also used to make rubber, plastic, and again, dyes, also pharmaceuticals, which is when I was using it. Initially, nitric acid is clear, and I have seen this with my own eyes. If you leave it out for any period of time, usually about an hour, it starts to turn yellow. And that's because it starts to decompose and it produces brown nitrogen dioxide gas. Pretty nasty, nasty stuff. Next is phosphoric acid. This is quite a weak acid. Phosphorus is an essential element for both plants and animals. Most of it is used directly for making fertilizers and animal feed. If it's diluted, it has a pleasant but sour taste. It's non-toxic, so we use it as a flavoring agent in beverages that need to be sour. And I've also experienced the use of phosphoric acid because after I worked in the pharmaceutical lab, I worked in a dairy lab. Because I'm from the Midwest, we have lots of cows in the Midwest, and I worked for the biggest milk producing and bottling company in the US. Again, in a factory, but it was a lab attached to the factory. I had a lot of different jobs, including taking samples from the homogenizing machines upstairs where they would clean with the phosphoric acid, but I had to test the cleaning solution afterwards and make sure there was no milk particles or proteins or fat left in the tanks. I also tested the raw milk that came in straight from the farm on these big trucks. They would put some of the milk in a little baggie for me, and then I would test it to make sure it didn't have any hormones, make sure the cow wasn't on any antibiotics, make sure it wasn't infected with bacteria or anything, make sure to check it for fat content, all that kind of stuff. A lot of different things, including testing the bottles, is like a whole lot of stuff involved in that. Super boring job, but now that I think about it, I was responsible for a lot of different things. Anyway, and then we also use phosphoric for making detergents again. So obviously detergents are very heavily based on acidic compounds, or at least being made with acids, and ceramics. Next is hydrochloric. Obviously, speaking in biological terms, this is the acid that is in our stomachs. This helps to create an acidic environment for pepsinogen to turn into the enzyme pepsin, which helps to digest proteins, but it also helps to kill any pathogens or any contaminants that might be in the food that you eat. In industrial situations, hydrochloric acid is used to what we call pickle iron and steel, which is to remove surface impurities. and it is used as a general cleaning agent. I do believe if you pick up, I think it's called Vixol. It's a cleaning product here. If they still sell it, I'm pretty sure they still sell it. I remember when I first moved here and I had no idea what anything was. Nothing in the grocery store was familiar to me at all. There's like no brand names, nothing that I recognized. So I just picked up something that was in the bathroom tile cleaning aisle, and I was cleaning my bathroom, and my husband was in the living room and he said, "What are you doing?" I said, "I'm cleaning the bathroom." And he said, "Well, there's like blue smoke coming out of the bathroom." And so I was like, "Really?" So I leave the bathroom and I kind of look in. I'm like, "Oh yeah, there's like, it's quite fumey in there." And when I looked at the back, it turned out that this Vixol, this liquid that I was using, is like 10% hydrochloric acid. I thought, oh my God, it was actually not digesting, but it was actually, what do you call that? It was eating away the grout in between the tiles. So I like quickly tried to wash it off. Hydrochloric acid is used in food processing. It's also used in oil wells, recovering magnesium from seawater, making other chemicals. Now, dilute solutions of hydrochloric acid are called muriatic acid. I don't know why they have to give it a whole different name instead of just saying dilute hydrochloric acid. You can find this in hardware stores. It is used to maintain the correct acidity in swimming pools, and it's used in cleaning stone. I've actually seen my husband use muriatic acid to clean stone because that's his industry, which is natural stone. There we go. So I do remember that. Vixol is hydrochloric. And finally, acetic acid. I want to make sure I can get to bases in the next 10 minutes. Acetic acid, probably the most easily identifiable acid based on its smell because it is vinegar. Vinegar is a very dilute form of acetic acid. Concentrated acetic acid is called glacial acetic acid, and that word glacial comes from the freezing point, which is 17 degrees Celsius. So if you have like a really cold room, acetic acid will freeze. The fermentation of certain plants makes vinegars containing acetic acid. So the white vinegar that we use in food is between 4 and 8%, which is what gives it the sour flavor. The most important use of acetic acid is in making plastic. It's also a raw material in the production of food supplements, for example, lysine, which is an essential amino acid. And it's also used as a fungicide. I have to remember this because I think the rainy season is close to being finished. It hasn't rained for a couple days, I think. And I'm getting a bit of mold on my concrete outside of my driveway. So just like making a mental note, I can use vinegar. All right. And then finally, I just want to finish up with bases. Bases are bitter tasting. If you've ever accidentally had soap in your mouth, or I don't think parents do this anymore. I had my mom's youngest sister. She's only 5 years older than me. So she was basically my older sister growing up. And I was being a smartass one day. I was taking a bath and I was teasing her. And then she said, "If you do that one more time, I'm going to put a bar of soap in your mouth." I didn't believe her. So I was just like, blah, blah, blah. She actually stuck the bar of soap in my mouth. And then I started crying and my grandma like spanked her. So I was like, hey. Again, don't use taste as a test. Now, I mentioned at the beginning, there was a word for destroying tissue and skin, but we use different words for acids and bases. Acids are corrosive, bases are caustic. So this is the word that we use associated with bases. Again, it means the same thing. So I mean, the effect is the same, but there are two different terms so that we can distinguish between acids and bases. Again, bases change the color of acid-base indicators. Excuse me. The color that's associated with bases is blue. So again, the same picture of the left where we had a vinegar with a strip of pH paper, which is universal indicator, turns red, with sodium hydroxide turns blue. It's also an easy way if you ever get asked about litmus paper. We don't generally use litmus anymore, but there's red and there's blue litmus. And so if you ever want to try to distinguish between which type of paper you use with which type of solution, just remember red is acid, blue is base. You're obviously not going to use red litmus paper to turn red. So you're not going to use red litmus paper for an acid. You're going to use it for a base and vice versa. Because acids turn blue, you're going to use red litmus paper. Sorry, I just said acids turn blue, I think. Bases turn blue. So you're going to use red litmus paper to see blue. Acids turn red. You're going to want to use blue litmus paper to turn red, to check for that. 3, dilute aqueous solutions of bases feel slippery. Of course, we have all washed our hands with soap. You might have actually made your own soap with Teacher Vanessa for like science fair day. And there we use lye. And the reason why soap works the way it does is because it actually turns the top layers of your epidermis into soap, and you literally wash those layers away, revealing clean epidermal layers underneath. Same with acids, that acids react with bases to make salt and water. The reverse is also true. Bases react with acids. That's the same thing. And again, if bases are strong bases, they will ionize completely in solution and they can carry electric current. If you have a weak base like ammonia, it will not ionize as much. And so it will conduct a little bit of electricity, but not a lot. And that's okay. I'm not going to start Arrhenius today because he's one of the first scientists to define